When deciding upon what our project should entail for this quarter, all four of us, Drew, Joey, Matthew, and Jack, went to work brainstorming different ideas that had to do with flying objects. After a period of discussion and conflict, we came up with the idea of a catapult. The project was approved and we went to work. As a group, we decided to set our standards high, expecting to send a projectile over 130 yards with extreme accuracy. We decided that our design, using rope as our force of propulsion, needed a strong frame to endure the stress on the structure.
Therefore, we took a trip down to a metal fabricator that we knew well to acquire 1/4 inch steel scrap metal and a few other miscellaneous items that we would need to accomplish our task. After this, we then took a trip down to Home Depot and got necessary materials: wood, rope, screws, and all other items. After being fully loaded with supplies, the building process was underway. To much of the surprise of the group, there was little difficulty and very few issues arose. After a few hours of building, the project was now ready to be tested. The first few test launches exceeded our expectations as far as distance is concerned, but the accuracy was not where we had hoped it would be.
We realized this might have been due to the hand release of the catapult arm. We decided that we needed a more consistent way to launch. Therefore, we installed a trigger system and went back to the test site, only to discover that our previous issues with accuracy were mostly solved. We proceeded with 5 more launches and recorded the data. Joey, you may end the video.
Yeah.
3, 2, 1.
Jack Sherlock here presenting data collection. Now, to first start, we're going to look at the goals of the project. Our distance that we wanted to achieve today was 130 yards and 118.87 meters. This was the goal we set at the very beginning of the project. Now, this is just distance. Another component of that, of course, is accuracy. Our original goal was to be within 15-foot radius in 5 launches. Now, looking at what we achieved today, we had an average distance of 143 yards and 130.76 meters. That's not even our best launch right there. Our best launch reached over 200 yards, 2 football fields. However, we had an issue. The accuracy was not there with that amount of force on the rope. So we had to tune down the force a little bit on the rope to become more accurate. So with our 5 launches today, we had an average distance of 130.76 meters and an average time of 5.42 seconds in the air. This equation right here will give us the average horizontal velocity. And in the end, we calculated a grand total of an average velocity of 24.125 meters per second. Now, a lot of you guys are confused right now. You don't know what's going on, and neither do I. So I need a diagram to help me out. So, our diagram right here explains it all. We have our catapult, beautifully drawn. And we have our golf ball in midair. People might ask, like, Jack, does mass matter on the golf ball? And the answer is no, it does not. So, golf ball flies through the air, and we have 5 X's marking the points that it landed today. Inner circle has a radius of 15 feet, our original goal. However, there's 3 outside that circle, so we can accurately say today that our accuracy was within a 22-foot radius of each other with 5 different launches. Thank you.
The first physics topic that we will be discussing is torque. The rope in the catapult was turned by a torque wrench to a specific torque before each launch. At the set torque, we found the mass needed to hold the arm down at 90 degrees. This mass was measured in pounds, which was then converted to kilograms for the purposes of finding the torque at the end of the throwing arm. The mass in kilograms was multiplied by the acceleration due to gravity to calculate the force acting at the end of the arm, as seen here. We then measured the length of the throwing arm, which is the radius used in the equation right here. Since the mass at the end of the rope is perpendicular to the throwing arm, the theta value in the equation is 90. When you plug all the values into the equation, the result is 218.8 Newton meters, as seen here.